Cool. And I'm going to kick us off. So today we're going to be talking about interpretability of LLMs. In particular, we're going to dive a little bit into the paper that Anthropic released a few days ago. It was starting with some caveats, as always. I'm not an expert in this field. I don't know how it is in interpretability, neither am I an expert, but I've read the paper and some previous papers from them. Of course, there's limited time to prepare for those sessions. We have other things to do. It's quite a complex topic, as this is just one of many approaches you can follow. And we're not going to cover the other ones. And we're going to cover this one in an oversimplified way. My goal is to pass over the main points from the paper, and then there are a lot of nuances and buts if you want to dive deeper into the paper and the links I have in the presentation. Okay, with all those caveats in mind, we're ready to start. There are two sections to this. One is the problem that we're trying to sort of solve, and the other is what the Anthropic team found. So let's start with the problem. So the first important point in this conversation, and a natural way to start, is by describing this notion of polysemanticity. Essentially, it would be ideal if in a neural network or an LLM, we could go into a neuron, and that neuron represented one concept, and every neuron essentially represented one concept. But that turns out not to be the case, a phenomenon that we refer to as polysemanticity. And one way to see this visually is, for example, in this image I shared from the Inception model, where there is a particular neuron that fires for both cars and cats. But the same phenomenon happens in all kinds of neural networks, including LLMs. So the main thing to keep in mind, just to start us with, is that the neurons themselves do not represent single concepts, but many concepts. And this on itself is what we're trying to solve. It's hypothesized that this is because of a phenomenon called superposition. What is superposition is nothing less than the fact that there are many more concepts to represent, and there are neurons that we've decided to have in the representation. And as a result, some compression needs to take place from an ideal disentangled model, so to say, that would have all the concepts as neurons, to the actual model we're training that has less neurons and such, but the same representational power. So some sort of compressing needs to happen. And this is what we are observing in the neural networks. So the Anthropic team lays down 3 ways that you can go about the problem. This is not an exhaustive list, of course, on how you can tackle the problem. But it just offers 3 sort of avenues that come to mind also instinctively if you think about it. With the first one being, what if we train an LLM to actually have this sort of monosemantic representation? What if we force it by forcing sparse activations? Now, they actually said they try to do that quite intensively, because that would be quite a nice solution to this problem, but they offer some sort of motivation as to why they think this is not possible. And the easiest way to describe that is by thinking one neuron, like in a very simplistic case of one neuron that tries to represent 4 concepts, predicts A, B, C, D. Essentially, if that neuron predicts A all the time, the loss is going to come out to be higher than if it predicts A and B uniformly, and then the rest uniformly, which is to say that there is a benefit to sort of create polysemantic relationships anyway, even in this very simplistic scenario. So it might also be the case that if we're trying to train a large disentangled model by enforcing sparsity, even in those cases, the model might be incentivized anyway to represent things polysemantically. So they gave up on this first approach for this reason. So the second one would be to use some sort of strong dictionary learning approach. There's a long literature on dictionary learning. And what they say quite succinctly, like they don't dive into it, is that all their efforts on that front overfits. Plus, they feel that this is a strong assumption to take when trying to learn these features. Instead, they sort of advocate for this hybrid approach that sort of combines the two. So let's see what this approach is. It's quite a simple approach, so that's convenience. It's nothing more than a sparse autoencoder. That's sort of quite similar to the neural network itself. So that's like one reason why this is useful. But it also scales quite nicely, because there's a lot of work on how we can scale those networks. So it sort of brings those advantages into it. And basically, the way this works is you take one layer or even all layers of the neural network. You take the activations, like you can think of a transformer sort of a stack layer and a series of sort of feature vectors that come out of it. And you pass in a data set from the neural network, and you get like a set of activations. Say, for example, that each feature is represented with 512 dimensions, or 1024, 2048, it doesn't matter. You get a set of those features by passing the data from the network, and this is your training data set. You stack that up and you pass it from a sparse autoencoder that has a middle layer that is the dictionary size, the features, the concepts you're trying to extract. And you force sparsity into that, as you do with sparse autoencoders, in the hope that those concepts will be meaningful and distinct to one another. It's quite simple to train that, like it's a simple loss term that sort of tries to reconstruct the input, plus a sparsity loss, because we're trying to make things sparse. There's a little bit of a conversation where I'm going to cover as to what is the coefficient on the sparsity, which makes things work versus not working. But then having done that, you can then take situations where the features of the sparse autoencoder trigger and not trigger, and then use some sort of auto-interpretability method to name them using an LLM to say, okay, this is related to this concept. So this is the methodology in a nutshell. You can read more into it into this paper, which is not the Anthropic paper, but another one that is quite sort of a simpler way to dive into it. It's also worth saying that there's a little bit of theory behind why this is a good idea that sort of connects autoencoders with behavior in the brain. And some conditions that are mentioned in that paper are sparsity, which is what sparse autoencoder does, and non-negativity. So there seems to be some theoretical background to this, even though it's not necessarily sort of a proof on itself, but there is some theory behind it that validates the use. And it's also worth saying that this is a hard problem, right? Like I think up until this point, maybe we've underestimated what we're trying to do. So it's worth saying that what they're trying to do with interpreting the model is a hard problem. First of all, it's a hard problem because, like, visualize it in this image that I showed. It's a projection on a higher dimensional space into a lower dimensional space. So we can think of it as a 2D projection of a 3D model, but it's actually harder than that. And we're observing the 2D. Of course, inverting that into the higher dimensional is not a trivial thing to do, and it doesn't necessarily have one solution. The only way this might be possible is because of the extra constraint we're adding, essentially the sparsity. But it's a hard problem, and it actually has a similarity to a well-studied problem called compressed sensing, for which there exist a lot of algorithms that provide, the problem is NP-hard, another reason why this is hard, and there are a lot of approximate algorithms for that problem, none of which the Anthropic team used because they said the sparse autoencoder has these other benefits that we talked about, but it sort of says that it's a well-studied problem with some approximate solution that we can take inspiration from. Cool. Okay, so this is the scene being set up for diving into what they found. So what they found is quite fascinating, and this is just a simple list of single and more complex features. So they started on a few years ago by doing it for a one-layer transformer block, and on that simplistic work, they found features such as Arabic letters, DNA, uppercase, and they continued that work by doing the same process. Claude Sonnet, which is kind of like the medium range model. They did it on the middle layer of that model, and they found further both simple features, so simple things like cities, different cities, celebrities, etc., but also more complex features as you would expect from a larger model, things that would represent something like a coder, gender bias, and sickness. So they found a combination of simple things, as you would expect, and more complex things, which is super interesting. One way to visualize those the features that they've identified, these graphs that they share quite a lot if you dive more into it, and they show how those features are activated based on different texts. And in an ideal world, this would sort of represent a calibrated probability where when it's highly likely that if, say, for example, Arabic, it would be quite high as it is here with red. But on the low end, you wouldn't have this sort of blue noise, so to say. You would just have less sort of red when it's less sure that this is Arabic. That being said, they do mention that this might be a product of either, as we're seeing here in this example, mention of some Arabic combined with other things, or just a method, big not the perfect method to recover monosemantic features. But this is one way to visualize it and sort of offers sort of some sort of proof that this is working. Of course, it's worth asking the questions. It's worth being a little bit skeptical about this. So there are a couple of sort of investigations that the team did worth mentioning. First of which is, are those features actually individual neurons within the network? So are we able to recover features in the case where neurons happen to represent only one concept? As a counter example to that, as a proof that this is not the case, they found the most correlated neuron, and this is an example of that. The most correlated neuron to, like this Arabic one, triggers where we see the blue line is, whereas the Arabic sort of tokens live somewhere else. So this is to say, we're not simply cherry picking neurons that are monosemantic in nature and basically making them features. Another interesting finding is that as they scale up the sparse autoencoder, from having like a 1 million, say, features or dictionary to 4 to 34, they find more and more terms, and they find them in the frequency that they appear in the training data. This is quite interesting because like it sort of shows the kind of size you probably need to represent a concept. So say, for example, a concept appears once every 1 million times in the text, something like a city, for example, it means you can probably recover it with a 1 million representation because it appears with that frequency. But if it appears 1 in a billionth time, you probably need 3 orders of magnitude larger feature space to have the possibility of recovering it in the first place, which is both intuitive, but like also interesting that it comes. Another interesting finding, and also intuitive, but it also comes through, is the fact that as you increase the size, the features themselves, which are more sort of abstract, not abstract, but sort of cover broader categories, say in the 1 million case, they become more and more specific. So there are two ways to visualize that. One on the left, and you can see that later, but sort of like the gray represents like the 1 million model, and then you can see sort of the greens and blues inside, sort of splitting into more and more features. And also on the right, where you see the run from the initial model, sort of splitting as we increase the size into more and more refined concepts. So this is also interesting. What's probably though the most interesting is the fact that with those features we can still behave. as if all of those things I said were not proof enough. I think the biggest of the proofs is the fact that we can use those features that they found and named to steer behavior according to those features. So so first of all, it's worth asking how we can do that. And the answer is you have to project back into the neuron because if you remember, the neuron is polysemantic. So we need to change that feature by increasing its activation and project back so that to steer the behavior. And one example of this is this code there, where we pass in, if we amp it up, if we amplify the feature, we can sort of pass code that works, and then it's going to return something that doesn't work. And also, interestingly, if we do the reverse, if we pass a code that doesn't work and tune it down, it corrects the code. So this is just one example, but there are many, such as, for example, lying to us, deceitful behavior. So there is both a risk with that finding, but also an opportunity to sort of ensure safety of those models. Cool. It's worth asking the question, as I sort of hinted previously, how much of all of this is being explained, because we saw this graph that sort of sometimes it sort of misfires, and we need some sort of way to know whether this is working and to which extent. There's no perfect metric as far as I've seen this from the paper, but in the one layer transformer, one way to sort of quantify that would be how much loss was recovered. 94% of the loss was recovered, not a perfect metric from what they're saying. In the Sonnet case, the variance explained is something around 64%. It's worth saying that both of those sort of tie nicely with the feature presence we said previously, such as we do need higher and higher dictionary sizes to cover less rare concepts. So it's not very unsurprising that not everything is being described here, and that probably it can be described as the size increases. Cool. The last point to mention is it's worth asking the question whether the features that are being found are unique. Like, what if we sort of did the analysis again, or did it differently? Are those features about Arabic and DNA and so on and so forth features that generally show up? And the answer tends to be sort of yes. So they did find a lot of features that sort of are correlated between different runs of the models. They trigger samely, the sort of high correlation, and also counter to the fact that is that because neurons are correlated within the network? The neurons themselves were not correlated, but the features that they extracted were, which point towards some sort of soft proof or no proof indication that those features are probably more universal than not. And it also ties nicely with another paper that came up recently that sort of goes along the same line, that the larger these models get, the more similar capabilities they tend to find. Anyway, this was everything. There is a little bit of time for questions with all the caveats I mentioned in the front in mind, but I'll go for it.
A great question, but I thought it was a really cool paper. The steering thing was very impressive, and I'm not aware if that had been done in that form before, like steering features and changing the focus of the model.
Yeah, I think it mentions a couple of prior literature to that, including the one I shared, which is from that paper that I think is easier to follow.
You mean the first one, like the towards monosemanticity?
But also this sort of slide with the sparse autoencoder sort of links into a paper, not from Anthropic, that the equation I shared comes from. I don't think the steering of behavior has happened in an LLM. I think it might have happened in smaller models. I don't think anyone has ever done it in a structured way in an LLM other than prompt hacking and things like that.
To me, it feels like this opens up like some applications, possibly. I mean, maybe nothing groundbreaking, but could be useful.
Yeah. Of course, to go through, I mean, unless so if you're working with an open model and no one has done the feature interpretability work,
Yeah.
This is quite expensive to do.
Yeah.
But assuming that someone did it, or even that sort of this becomes like an API layer, like a property, yes. Any other thoughts, questions?
Also,
it's worth saying. Yeah,
sorry.
go on.
Just wanted to say, pretty good summary as well. I mean, I also just like, I wouldn't say I skimmed the paper, I read it, but like a lot of details that I didn't get, and I would have needed to spend more time on that. But I think it was a pretty good summary of how I understood it as well.
Good stuff. Yeah, it's worth saying that all of these materials are 200 plus pages long and multiple papers. And I hope I did justice to them. Cool. If we have nothing else, we're on time. 5 minutes.
Right.
We can continue the conversation in Slack. The link to the presentation is in the reading group. I added the meeting, and I also have a task which is linked in Agile, but I'll copy paste it anyway in the reading group channel as well. So there are a couple of ways to find it later.
Awesome. Thanks, Nick.
Sounds good. Thank you.
Cool.
All right.
See you later.
Thank you, Nick.
Bye, guys.
See you.
Thanks, Nick.
Bye.
See ya.